Thanks, folks. It's a really exciting time in this particular area. There's a lot of things going on right now involving water on the moon and Mars and the kind of research and tools we're bringing to bear. Some of them happened at 4 a.m. this morning, and one of the missions I'm going to talk about did a maneuver. I was glad to check my email and make sure that it went okay. So this is about water, and water is an important and interesting question as we explore the solar system and ask ourselves questions about where life came from. And I'm being reminded by our guys to turn on the microphone. Is that better? Yeah. Okay. Thanks. So part of this is a story about water, and just a little bit about where it might have come from and how it originated and how it distributed itself around the solar system, in addition to Earth. And some of the missions and scientific observations we're using to try and understand its dynamics and its importance. We all know that water is important on Earth, and so I hope to educate you some really specific detail about two planetary bodies, the Moon and Mars, as well as kind of give you a tour around the rest of the solar system to show you how commonplace and interesting this particular compound is. So, one of the prime motivations thinking about water is because, as many people understand, it is essential for life as we know it. All the life that we've understood here on Earth involves water. And where you find liquid water, life flourishes in almost any extreme environment, from the bottom of the ocean up to incredibly salty and or acidic tide pools, isolated locations where you have very cold water, you find life. Water is the thread that runs through all of that. So it's an astrobiology question to some extent, but it's also an environmental one and one that we can measure using physical techniques. It's also, from the perspective of agencies like NASA, an important resource. And if you believe in the idea that at some point humanity is going to expand into the solar system, you want to take advantage, ideally, like earlier explorers on Earth, living off the land if you can. It's really expensive and difficult to bring heavy things like water with you. And so the idea of using resources that are already there on the moon, or more likely, maybe on Mars, and understanding where water is and what state it's in is important. So the way to think about water in the solar system is that it holds some clues about life, and thus our own origin, and also, if you believe that we are going to expand, about our destiny to a degree. So that's why I find water interesting. It's a great theme that runs through all these fantastic questions and touches upon science and exploration. So now that we've got the feel-good big picture down to the nitty-gritty, how do we do it? What kind of questions are we able to address at this point in humanity's exploration of the solar system? I'm going to talk about two missions that are examples of this. One is called MAVEN. That stands for the Mars Atmosphere and Volatile Evolution Mission. The volatile part is where the water fits in. Water is a volatile compound. It goes from solid to liquid to gas and back again pretty dynamically. And another one that's going to touch upon the water question for the moon is called LADEE. That's called the Lunar Atmosphere and Dust Environment Explorer. Now, I said the word lunar and atmosphere together. That may be a surprise to some of you. The moon does have a tenuous atmosphere. I'll talk about that. And both of these have pretty strong UC Berkeley environment involvement, so I can describe to you what we're doing here and up at the Space Sciences Laboratory to help these missions along. So before I talk about those, let's take a quick go back in time to, well, what we think might have been the beginning of the solar system, when we were just a big plane of gas and dust, a protoplanetary disk, early young sun in the middle, all kinds of gas and dust and little planetesimals around that will eventually coalesce and form the planets as we know them today. Every bit of evidence we have says that water was really commonplace in this environment. And the interesting thing about water, H2O, is that it was one of the first to condense out of gas. And it formed this thing called the snow line inside this big disk of gas and dust. And that was probably, I mean, again, we can't be sure, but roughly at around 5 times the distance from the Earth to the Sun is the position of the snow line. And so that had a big bearing on how the planets formed, both within the snow line and beyond the snow line in terms of their supply of water, what kind of water they got. But everything we know says that water was pretty common. And so we know the situation today. We are fortunate.
Where does the evidence for that snow line come from? I've never heard of it. Is that mathematical analysis?
It's a combination of looking at the composition of the oldest objects we know about, comets, okay, Kuiper belt objects. It's modeling, some totality of everything we think we know about how planets form, looking at asteroids. So it's by no means completely certain, but it's our best understanding today that there was this idea about the snow line. Maybe we can, get better with extrasolar observations. We'll catch these protoplanetary disks in operation. That would be some confirmation. So then, moving ahead to where we are today, we've got the best example where we are right now. Pointed out earlier, lots of liquid water outside today. The Earth is unique because we're in this region called the habitable zone. That's where water exists in all states, as an ice, as a liquid, as a vapor, and it goes back and forth between those pretty readily. And we have a lot of water on the Earth, but the rest of the solar system, not so much. Liquid water is turning out to be fairly rare. It's easy to find examples of water vapor, water ice, but the amount of liquid water we have here right now seems to be somewhat unique. So let's think about water. You ever wonder how it got here, where it comes from? Well, we have a lot of it. Certainly we take it for granted. Let's think about water itself. Most people know water is H2O. You ever wonder why this really important substance is H2O? Hydrogen and oxygen? I don't know. I started to think about it. I thought, okay, well, let's look at hydrogen. That's actually pretty easy. Most of the universe, most of the material we know of is made of hydrogen. It's very common. 75% of the material is made of hydrogen. And the next most common element, helium, okay, the other 20-something percent. But helium's problem is that it likes to be alone. It's very non-reactive. It's an inert gas. So you go down the periodic chart, and one really plentiful element is oxygen. And the other thing that oxygen likes to do is it likes to bond to things. Oxygen is very reactive. So it's actually no surprise that the most plentiful element in the universe and one of the more plentiful and, more importantly, more reactive elements form a bond and form this common compound. You probably say that a similar story about other things like CO2 and others, but water is pretty special. It has this sort of dipole electrical property that makes it kind of semi-sticky. That's why you look at it in its fluid form and it behaves like it does. And it was also, like I said before, one of the first things to condense out of this protoplanetary disk and form the snow line. So it's formed an important role in planetary formation. Something that I need to get across to help you understand where we're going to go when I talk about Maven and Laddie is the detailed structure of water and a certain variant of water. So that has to do with how hydrogen atoms work. And a hydrogen atom is pretty simple. It's a proton and electron, the simplest and most plentiful element. There's kind of a variation on the hydrogen atom. It's deuterium. And deuterium is just like hydrogen, except that it has an extra neutron. It's fairly rare. Okay, something like 0.01% of water on Earth, you'll find a little bit of what we call heavy water. Okay, it's heavy because it's got an extra material in its nucleus. It occurs naturally. And this tells us a number of things. It can tell us, for example, what the temperature was when the water formed. We can tell that by the amount of heavy water that's in a sample. And the amount of heavy water in a sample can also tell us something about how water has been processed over time. And that's because they're chemically very similar, but this one weighs a little bit more. And that mass difference turns out to be important. And so if you come across a sample of water that has a lot of heavy water, that tells you that you probably lost a lot of water. And statistically over time, the lighter stuff left more easily. If you find a sample that's low in heavy water, that tells you that's probably pristine early solar system material, down to its native quantum mechanical abundance of heavy water. These are called isotopes. And so this enrichment in heavy water is something that's important to understand because that gives us an immediate clue.
What did you mean when you said quantum mechanical?
There's a certain natural occurrence of heavy water. that you'd find in the solar wind and what we believe to be the earliest solar system conditions. And to answer that question is a whole other talk. But we try and establish a baseline for what the earliest material was, and then we move from that. Okay, so let's take a quick walk through the solar system, just to give you an idea about various states and conditions under which we find water. This is Venus, and it turns out, unsurprisingly, there's a small amount of water vapor in the atmosphere of Venus. And incredibly, the amount of heavy water in that atmosphere is 120 times what it is if you look at water vapor on Earth. And what that tells us is that at some point in the past on Venus, there was a massive loss, a massive exodus of water as that planet evolved. That's the implication. When I talk about the Earth, we all live here, we know about it. The Moon, as some people may know, has recently been proven to have water ice, and I'll talk in detail about that. Mars has fascinated humankind for a long time in terms of the potential for water in the past and water that's present now. And of course, we do know that Mars has water, and I'll talk in detail about that as well. Interestingly, on Mars, it has about 5 times the amount of heavy water as you find on the Earth. And that hints at the ability or the prospect that Mars also, over time, lost its water through some process that we're trying to understand. The giant planets, gas giants, Jupiter and Saturn, they have water vapor in their atmospheres. And it looks like to be very pristine from the earliest solar system. It had very little processing at all. And then life gets a lot more interesting when you look at bodies like Europa and Enceladus. Those are moons of Jupiter and Saturn, respectively. Europa is a fascinating object. I'd love to come back and give a talk about that someday just by itself. Covered in ice, very likely has a liquid ocean beneath that. This is a key NASA exploration and science goal to go back to Europa and actually determine how deep that ocean is and what its properties are. Equally exciting is Enceladus, which has water geysers spewing out into space. So those are great examples of how small moons can have a lot of water activity. I already mentioned comets. Comets are about 80%, some of them, water ice, depending upon where they are and how old they are. And everyone knows about their tails, and that's ice and gas coming off as it gets closer to the sun. Beyond that snow line, which we still have today, but that's out at the orbit of Mars about now. It's come in a little bit as the sun has changed. The oldest asteroids also have a fair amount of water in them. That's one of the bits of evidence we have that in the earliest solar system conditions, water was pretty common. People will be amazed to learn that there's water vapor in the atmosphere of the sun. This was found in 1997 over a sunspot, which is a little bit cooler and just cool enough to make H2O stable. And when it gets to that condition, you can actually see water vapor. Probably delivered by these guys, comets, which are hitting the sun all the time. So that's a quick tour. Yeah?
Wouldn't one of the reasons for the water being less, more heavy water on like the Moon and Mars, and the fact that the lighter portion of the water has gone into space? Because Venus is hot, so that would force some of the lighter water off. And
Exactly.
less gravity.
And you just summarized the science goals for the Maven mission, which I'm going to talk about, lost to space. Now, the Moon, you mentioned, is having more heavy water. That's actually a fascinating topic, which I'm also going to touch upon. There, the story is a little bit different, if I can get to it. So, it's a good question, and we're spending your tax money trying to figure it out.
Get some back on the money.
Yeah, I hope. All right, so I'm going to start off with Mars. And from the first time we could see Mars through a telescope, it was pretty obvious that this was a body that had very probably had large amounts of flowing liquid something over its surface, probably water. There were all kinds of features that more than hinted at that possibility. Valley networks, for example, being one of those. Valley networks is something you only find where you have running water. They're all over Earth, similar to Mars. There's also very strong mineralogical evidence, minerals that can only be formed in the presence of water that the Mars rovers have found. We know that the polar ice caps, for example, contain a good amount of water ice. We've seen water sublimate and evaporate from the Phoenix lander. We detected water ice in the soil from remote sensing observations that extends beyond the polar regions. The atmosphere has water vapor, but Compared to Earth, this place is a super dry, high altitude, cold desert. If you were to take all the water from the atmosphere and force it to become a liquid on the surface, it would occupy 10 or 20 millionths of a meter in depth. So you'd end up with this thin veneer of water you could barely detect. That's 10,000 times less than what would happen if you did the same thing on Earth. So although there's lots of water on Mars, from the perspective of where we live, it is still incredibly dry. If you go back in time, and you ask yourself, okay, you've got all this evidence about how wet Mars was in the past. What happened? Why is it so dry today? What were conditions like in an earlier Mars? And one really plausible scenario is that the early Mars was warm and wet, and it may have had large oceans covering most of its surface, or the majority of its surface. And in fact, if you were to melt some of the polar cap material today, you could do a fair amount of filling over the surface of the planet. So, if there was an early wet and warm Mars, what happened? Why is it so dry today? Why did all the ice retreat to the polar regions, go into the soil, and or perhaps leave through some other mechanism? So again, we're really curious about this, particularly in the case of Mars, because Mars is one of our most likely targets for understanding whether or not life could exist in some other environment beyond Earth. So again, we know that liquid water is important. There was access to what we know as biogenic elements, carbon, nitrogen, other things like that life needs to evolve. So did Mars ever have life? How did that life interact with the environment? And how has the habitability of Mars changed over time? When you look at Mars today, it's not really that habitable because of the lack of liquid water on the surface, but the past may have been very different. Again, here are some more examples of how we know that there was liquid water in the past. Here's one of those valley networks I was talking about. You can analyze the mineralogy. You can find carbonate deposits. Again, that's a telltale signature of water processes. And getting to an earlier question we had, we also know from orbiting spacecraft around Mars that volatiles, of which water is one, can actually be lost into space from Mars. These are escaping ions. Ions are neutral atoms that have been ionized. So they get out into space and solar radiation kicks off an electron, they're ionized. And the solar wind, which is this electrically charged wind coming from the sun, just picks them up, blows them away. Why isn't that happening on Earth? That's another question. Why isn't it happening on Mars and not here? And one of the answers could be something to do with a planetary magnetic field. Now, we all know about the magnetic field here on Earth. It's what you steer your compass by. We have a north magnetic pole, we have a southern magnetic pole. You can imagine in the center of the Earth a big bar magnet, and that would give you magnetic field lines open and close around the planet. I mentioned the solar wind. The solar wind is this charged gas coming off the sun. And so it interacts with things electrically and magnetically, as well as physically. And on the Earth, our magnetic field is so strong that it acts like a defense shield. It actually keeps the solar wind from impacting our atmosphere directly, except in a few isolated locations. So, the same actually could have been true in the history of Mars. There's all kinds of other evidence from analyzing the rocks and looking at what we call remnant magnetic fields, that Mars, in fact, may have had an early, large-scale magnetic field like the Earth. And so it, too, would have had the benefit of this defense shield. But for some reason that no one understands, in the past, probably about 3.7, maybe even 4 billion years ago, this magnetic field collapsed. It disappeared. And now you're left with a planet exposed to the solar wind, unprotected. And once you're in that state, there are all kinds of processes that could theoretically, literally, blow the Martian atmosphere away over time. You can imagine that there's what we call a hypermagnetic process in which you're just, by momentum, pushing large chunks of the upper atmosphere away. The upper atmosphere gets ionized, and on Earth, that's not such a big problem, but on Mars, once it's ionized, it gets caught up in this stream of flowing solar wind. So that's the question that some of us are addressing. as part of the overall picture about the inventory of water on Mars. Yeah.
What's the UV?
Extreme ultraviolet. Yeah, and that's that thing that I'm talking about that ionizes neutrals. So there's a certain rate of ionization that creates our ionosphere, that creates an ionosphere on Earth, and it certainly creates an ionosphere on Mars, which is actually very much like the Earth, but Mars does not have the benefit of this magnetic bubble that's carving out this cavity in the solar wind. This is where MAVEN comes in. MAVEN is the last of the Mars Scout line of missions going to Mars, funded by NASA. It's led out of the University of Colorado by Bruce Joukowsky, who's a very well-known Mars planetary scientist. And we have a very big role here at UC Berkeley. We do a lot of the science with the charged particles and how those interact with the Martian environment. And we built the entire instrument suite that will address that problem. MAVEN is not launched yet. It's going to launch, I hope, in a couple of months. And it's going to orbit Mars and study this whole problem. Is and has Mars been losing its atmosphere into space over time? It's kind of like a cartoon that tries to encapsulate some of the different processes I'm talking about. So I talked about the solar wind. That's this charged gas that's flowing out from the sun all the time. And now you have this planet that it has a little remnant of its original magnetic field, but it does not have a big global field like the Earth does. And so it's left unprotected to this streaming, flowing solar wind. So there's all kinds of processes that can happen. One is that once something becomes ionized, this is the pickup process I talked about. Those ions just get picked right up in this flowing solar wind and carried away. There's also simpler processes that can happen. There's this thing called Jeans escape, and that's when things get hot. That just causes them to, by thermal energy, to gravitationally escape. There's also chemical processes that can happen. Photochemical escape is one of them. I can't go into detail on all of those, but the point is that when the planet doesn't have a mechanism to shield a lot of these effects, is the loss rate a lot greater. There's the extreme ultraviolet I talked about, which does a lot of the ionization. The other thing to realize about the sun is that it's highly variable. It goes through very stormy periods. And so another question to ask is, even if the rate from the average processes like the solar wind and the average EEV output aren't enough, what about when the sun gets excited? And it's also possible that during what we call a coronal mass ejection, which is a solar storm associated with solar flares, maybe most of the loss is happening during these episodic events. And the analogy is sort of, maybe it's a whole bunch of Katrinas that are decimating the atmosphere from the perspective of like having a hurricane as opposed to the average. So MAVEN's looking at all those questions. Fundamentally, what MAVEN does is it gets to Mars and it measures many of these processes that it can. It tries to count every atom leaving Mars using a whole series of detectors. And we do so while paying attention to what's happening at the sun. We try and correlate those two things to understand the underlying mechanisms that cause this material to leave.
So you've been focusing on outgoing water and all this.
Yes.
Incoming water.
Yeah, that's a valid question. In fact, I was just thinking about this a week ago. A postdoc that I hired is looking at the delivery of interplanetary dust, a lot of which is ice being pulverized off of the Oort cloud and Kuiper Belt objects. So far, that's not a significant source. It's sort of less by an order of magnitude, but it's an important question and one we're keeping an eye on, because you do have to account for the sources and sinks. And on that question, there are other places the water could have gone. It doesn't have to all get lost in space, because the other end of this whole water budget is water going into the soil and into the polar caps. And so, admittedly, MAVEN is just looking at one piece of this overall puzzle.
How well understood is the process this planetary magnetism on Earth and others?
Yeah. What we know is that Mars does not have a global intrinsic field. You will find a lot of debate about how and why and when it failed. And so that certainly affects our ability to extrapolate back in time and estimate the evolution of the atmosphere over time. There's a lot of work that's been done in dating materials that are magnetized and those that aren't, and that's fairly definitive. And so that's a pretty good constraint that it happened a long time ago, early.
On Mars.
On Mars, that's right. When you talk about the Earth, there are questions about, potential pole reversals and things like that. I can't touch that today, but, it's an open question. How and why a dynamo works the way it does, yeah, I think there's a lot of questions there.
And do you know, does Mars show oscillating north and south polarities like we see on Earth?
I'm not aware of any direct evidence for that. I think that the focus has been on it died and why. Yeah, so far, we have to go back 3 or 4 billion years just to get to that point. So.
Do you believe it escapes moisture and water from Venus and Mars in our atmosphere and ocean?
It's possible. I'm going to talk a little bit about where water on Earth could come from. There is an exchange of materials across the planets, I believe. There's a lot of commonality. And this question of heavy water is one of the ways to try and get at that. Almost certainly, just through Martian meteorites, we've gotten some water. That's not very much. Okay, so here's Maven. Here's the business end of how we get this job done. This is a spacecraft that's fairly big. I'll show you how big in a minute. It's based on a orbiter that's currently around Mars now called the Mars Reconnaissance Orbiter. So this is a big remote sensing class spacecraft built by Lockheed Martin and instruments provided by University of Colorado and UC Berkeley. And so we have a whole array of instruments, all of which are designed to measure all of these low energy particles and ions coming off of Mars and looking at also solar conditions during that time. It's solar powered. It's got a big communications dish here. It's got this little boom and an instrument package on the bottom that steers and measures particles in different directions. And it has a number of smaller sensors mounted on the body. It's about the size of a school bus once it's got its solar array deployed. It's the same weight as a fully loaded SUV with all the kids and groceries. It's going to launch, I hope, sometime in November 18th to December 7th. Yeah, that's just a little while. On a big Atlas V rocket. It's going to take about a 10-month cruise to Mars on a typical trajectory. And we hope to insert in orbit around Mars in September of 2014 and go through a Mars year of science operations, which is 2 Earth years. Important to get that straight. And it's going to be in what we call an elliptical orbit that looks at the space environment around Mars at varying altitudes. And as it does so, it's going to sample all kinds of different regions around Mars. Mars doesn't have this global magnetic field, so a solar wind impinges directly on it, and it forms different interaction regions called the sheath and pilot, and then it leaves sort of a vacuum wake, much like, if you're moving fast through the air, there's a wake behind you. Same thing in the solar wind. And again, all the while, we're measuring all these particles coming off of Mars under different conditions and correlating that with solar activity. And then we add it all up, and we see how much of it can account for over time.
Is this sort of shock from the incoming solar wind or from Mars'
Yeah.
orbit?
So the solar wind is coming this way. And so the sun is, 10 miles that way. Then this is the anti-sunward direction, so this is the shadow and the wake region.
Why is it limited to one Mars year?
Money.
Because it seems like you could take a long period.
Yeah.
Right?
Let me put it to you this way. The spacecraft has the ability to last at least a decade. And the other thing we have on is a transponder, which we're going to use to relay communications from the surface. We also become an orbiting communications satellite asset. NASA, once a mission proves itself and we get good data, we usually get a mission extension. So I would hope that we get a decade of excellent measurements out of this guy. Write your congressman, please. Solar variability. I kind of made this point already, so I won't spend too much time here. Maven is flying to Mars and going to be operating at a time when the sun is reasonably active, and what that's going to give us is a wide dynamic range of solar conditions in which we can correlate atmospheric loss processes. And so here are the science instruments. This is really where the tire hits the road for us experimentalists who are involved in this work. And the part that Berkeley's doing is this whole suite of plasma and field measurements. Now, I said the word plasma. I don't mean blood. Plasma is another term for charged particles, ions and electrons that compose most of the material in space. And a lot of the material coming off of Mars because it gets ionized as soon as it gets into space, or becomes ionized by some process and then it's kicked off into space. And so these are particle analyzers. They actually directly measure these incoming particles, determine their mass, energy, where they came from, what their spatial distribution was. Over really energetic particles that are from the sun hitting Mars, and then more energetic ones coming off. And then the ion and electron guys look at the lower energy stuff coming off the Martian ionosphere. I'm involved directly in building and implementing this one. This is a plasma probe that actually measures the lowest energy electrons that are barely moving. We suck them in like a current. That tells us how many of them were there. We add that all up together, and that gives us a really complete coverage over all the different populations of particles that are going to be streaming off. There's also worth mentioning an incredibly complex and capable instrument called a neutral mass spectrometer. So we catch the neutral particles, the atoms that didn't get ionized, as well as the ones that did. And this is from the Goddard Space Flight Center.
How big is that? It looks like it's the size of an ice chest.
Yeah, it practically is. It's one of the major instruments that's down in that articulated boom. It's I'd say it's the most complex instrument we have. Inside of that thing looks like Rube Goldberg plumbing experiment.
What's meant by suprathermal?
So a thermal process is one in which you can define a temperature of something, okay, and that has a certain implication about how that got excited, and that's thermal process is your pie being hot when you take it out of the oven, all right, but then if you shot that pie with a particle beam and stuff came flying off really high energy, that's a superthermal process. It's being energized by something that's not thermal in nature. It's energy being imparted but in a different way. It's more energetic typically. And one of the questions that Maven's trying to address is, thermal processes in terms of contribution to loss versus superthermal ones, which is most of how the solar wind interacts with Mars. That's a whole class of superthermal activity. That's what Maven looks like, being built up in the clean room, big communications dish, a whole bunch of pipes and wires and all kinds of stuff that keep the spacecraft working. This is before most of the instruments have been put on. That's Maven in testing. We expose it to loud noise and vibration to make sure it's not going to shake apart during launch. We put it through the cold vacuum of space and high and low temperatures. This is just before getting packed up. Solar arrays are installed. If you ever see a spacecraft up close, it looks like it's in saran wrap or tinfoil. It's nothing like you expect. That's for thermal reasons. You don't want the thing to burn up in space, which happens or get too cold. This is our big rocket. This is the Atlas V coming together at the launch site. There's the Maven logo. And that's kind of the point we're at now. Maven's at the launch site getting processed, about ready to get stacked onto the rocket. And we hope to launch soon and make some progress on this question about this unique mechanism for how water gets lost, perhaps, on Mars, and answer maybe all or part of the mystery for how water escaped over time. And if we do, it has a lot of implications for how planets work. For example, the question to ask is, what would have happened if Earth had lost its magnetic field? Or if we do at some point in the future? Would we also lose our atmosphere? So these are interesting questions, both from just understanding Mars and also general planetary science. All right, I'm going to leave Mars now. I'm going to go to the moon while I still have time. But any more questions on Mars before I do?
With the flipping of the solar polar magnetic fields that apparently
The flipping? Yeah.
Starting to flip, right?
Yeah, and I think that's another open question. I mean, the question I would ask is, the one I just did, was what would happen to Earth's atmosphere if that happened? And I don't know. It's kind of scary, actually. Yeah, so we haven't focused on that with respect to Mars that much. The first order question is, why did it go away entirely? If Mars still had a magnetic field and the atmosphere was still as dry as it is today, and we had evidence of volatiles that been lost to space, then we might start asking that question. Okay, it's still there, but maybe it flipped or changed throughout time.
Why
wasn't CO2 lost?
CO2 was lost, and I'm sorry I didn't make that point. That's actually another goal of Maven, because along with water, you need a thick atmosphere to maintain it. And so certainly in the past, there's evidence that the atmosphere have been thicker to maintain the temperatures necessary to support liquid water. Mars, by all accounts, had a massive loss of CO2, and there are all kinds of mechanisms that can do that. Giant impacts early in its formation. But there's a lot of evidence that other sources of CO2 came to replenish that. So the next question to ask is, what role did the solar wind and being exposed to space have? Okay, one more and then I got it.
Do you have any idea how much subterranean water there is in Mars?
Yeah, that's the other sink for water, and that's the other half of this equation. And so what Maven is doing is it's constraining the loss of space part. And I'm also involved, and other people are in research, in the going in the ground part. Very possible. There are models that predict how much water is in the subsurface. Depending on who you talk to, it can or it can't account for how dry Mars is today. But we do have direct evidence in the isotope measurement, this factor of 5 I talked about earlier, where we have more heavy water on Mars. That's what you would expect if it went to space, and not necessarily if it went into the ground. All right, I'll try and get through the moon in time, because we have another mission going on right now that's going to touch upon the moon and water. So first of all, how many people knew there was water on the moon? Yeah, okay, that's incredible. A decade ago, that wouldn't have been that much of a response. We have gone through an absolute revolution in understanding of how water works on the moon. When we came back from Apollo, we brought samples. And one of the first questions, okay, let's find the water on this dust, on these little lunar dust mines. And some really smart guys did an experiment down in Pasadena, and they found a thin layer of water on the surface of the dust grains. And what did they do? They looked at how much heavy water was there, and they found that it was exactly the same as tap water in Pasadena. And they thought, that's got to be contamination. And they concluded that all the water was contamination, that, despite their best efforts, a little bit got into the soil, and they concluded that the moon was bone dry. Okay? We're in a much different place today. However, people pointed out, okay, those Apollo samples were dry, but there are special regions on the moon that may be different. And those special regions are in the poles of the moon. And the moon has some really unique environments in the polar regions. That's because the moon is heavily cratered. Okay, it's got these deep depressions in its surface because of impacts, and there's no running water, there's no weather over time to erode them away. And that means that when you're in the polar region and you have the sun shining on you, and if you're inside one of these craters, there's a certain number of craters that in fact never see the light of day. They are always shadowed. They're called permanently shadowed regions on the moon. And those may be cold enough and may be stable enough to harbor water. And over time, there's been a whole flotilla of missions that have looked at this question, among others. Early calculations, sort of on a theoretical basis, since the 1960s, confirm that it's possible that if you have these really cold regions, in the same way that your tongue gets stuck to the cold pole in winter, once water enters that region, it gets stuck. It's like the Roach Motel, the water goes in, doesn't come out. And then we started getting better at sending relatively inexpensive unmanned spacecraft to the moon. We started doing experiments to try and figure this out. And there was a radar experiment on the Clementine mission in 1994 that hinted that there might be water ice in these polar regions. And then even stronger evidence came along when the Lunar Prospector mission flew. And Berkeley had some involvement in this. We built this thing right here, measured magnetic fields. Lunar Prospector came along and actually detected enhanced hydrogen in the polar regions. We couldn't detect water directly, but there was a lot more hydrogen. And that begs the question, is that hydrogen the H2 in the H2O? And because it was limited to just these permanently shadowed areas on the moon, pretty good possibility it was. And the Lunar Reconnaissance Orbiter came along, and that's still operating right now around the moon, and confirmed that in fact these permanently shadowed craters are some of the coldest places in the solar system. Colder than Pluto, in fact, just because of where they are and the fact that they don't see the sun at all and radiate to space all the time. And the proof in the pudding was this incredibly clever mission called L-Cross that happened just a few years ago, which they slammed a spent rocket motor to finally try and just unearth this stuff and figure out, yeah, is there water ice in there? and that was the detection we were looking for. So here's a view of the South Pole. This is a gigantic impact basin. It shows you the blue gets deeper, okay, and it shows you that you have all this deep stuff in the South Pole that can be permanently shadowed. It's really common. And here's an illustration of that. This is an analysis of the amount of sunlight that some of these polar regions get, and the black areas don't get sunlight at all. Here's an example from the Lunar Reconnaissance Orbiter of a crater that's mostly permanently shadowed. This is a high-intensity image that basically is looking at reflected starlight because there's very little light impinging on it. That's Shackleton. This is the hydrogen measurements I was talking about. It shows that you have these little blurbs of concentrated hydrogen in the polar regions. It was really tantalizing because we had all this sort of indirect evidence. Wow, we're getting really close. There's lots of hydrogen there. You know, is it water? And then a couple of things happened. We had 3 or 4 flybys of the moon of interplanetary spacecraft that had other destinations. And they did some observations of the moon during their flybys just to take advantage of the opportunity. And they put all that data together, and what they discovered was, in fact, that thin layer of water that those guys in Pasadena thought was contamination. Well, guess what? It's still on the moon. It's this blue stuff. That's a thin monolayer of water on the surface of dust grains and particulates on the moon. So there's water existing on the surface, and it gets more numerous and concentrated as you get towards the colder polar regions. And then, of course, I already mentioned L-Cross, a really clever idea by my colleagues over at NASA Ames. They took advantage of the rocket that was launching the Lunar Reconnaissance Orbiter. They hitched a ride, and they built this little shepherding spacecraft that steered the spent rocket stage towards the moon and slammed it into one of these permanently shadowed cold craters. And they looked at the ejecta that came out. And what did they found? They found 12 buckets total of water ice. So that was finally the confirmation that, yes, the hydrogen is water, and there's a significant amount of it, and it exists in permanently shadowed regions. The moon has water. Wow. Yeah, 12 buckets. I'll get to that. Almost done. Yeah, it is, right. And we're asking ourselves now, okay, how did it get there? What does this mean? Okay, we found water, now what? Why is this important? So just like on Mars, we want to understand how it got there and where it's going. And I mentioned these polar regions as being relatively stable in terms of their temperature. They're very cold, water sticks there. Well, that's actually a very simplistic picture. If you start to look at the totality of environmental inputs to the moon, you have micrometeorites, you have solar storms, which can change the picture a little bit. You have starlight I mentioned earlier. And there's not a given that water is actually completely stable in these polar regions. There may be loss processes still happening. And if that's the case, then there has to be something replenishing it. And so that's the question that I and others are looking at. Is there an active water cycle on the moon? And you ask that question also because the moon has an atmosphere. If you don't believe me, you're looking at it. It's nothing like Earth's atmosphere. It's very tenuous. It's collisionless, meaning that it's so tenuous that none of the other atoms see one another. The technical term for it is an exosphere, so it's this really tenuous atmosphere. This is sodium and potassium that's being kicked off the lunar surface by radiation, by micrometeorite impacts. And so one way that water can come in is from the solar wind, which delivers hydrogen, and this chemically interacts with the surface. And the water, like on a hot griddle, hops around the hot lunar day side, and most of it gets lost back to space, but some of it, statistically, ends up in these little cold regions. And once it does, it sticks there. So even though it's a small amount, over time it builds up. And so this is basically a lunar water cycle. This is a very compelling theory for how to replenish and keep that water going if we should find that the water is not exactly stable. Now Laddie is going to look at that question among several others. This is a lot different from the MAVEN mission. Costs a lot less. This is about the size of a Mini Cooper, weighs about the same. And its main job is to characterize the lunar atmosphere. And in the process of doing that, it may find this active dynamic hydrological cycle on the moon. I'm not used to saying those words together, but that may be what's going on. It launched on September 6th, and so far it's going great. The Berkeley role here is different. I'm the deputy project scientist. I've been with it since the beginning, and then people in my group have been selected as participating scientists, so we're forming part of the science brain for this mission, which is being conducted and led out of NASA Ames. I'm running out of time, but these are the instruments. That's the neutral mass spec. It's the same guy that did it for the Mars one. This one's a little smaller, but equally as complicated. There's Laddie again, getting packaged up, going through environmental testing, and here it's getting packaged up into the nose cone. This is the Minotaur 5 rocket, low cost, surplus intercontinental ballistic missile rocket. So we're swords to plowshares. We're using old missile technology for a better purpose. And there it is, taken off. And in fact, at just 4 a.m. this morning, I got an email that our major perigee maneuver to send us on the way to the moon successfully completed, and so I'm happy. Things can go really wrong with maneuvers, so that's good. Okay, so back to why we care. I gave you one view for lunar water. It's concentrated in these polar regions. It may be dynamic, it may be getting lost to space, and maybe other sources coming to replenish it. Or it could be, it could have resulted from when the moon underwent formation, and or it was delivered by comets early on in its history. Or it could be some combination of the two. The point I want to make is that it's an incredibly insightful process that tells us about the history of the moon. Now, you talk to NASA and they say, well, it's also a resource that people are going to use, but I think you'd be pretty upset if you had to dig a football field's worth of material out to get 12 buckets. That would not be a good way to spend your time. And so right now, as a scientist, I'm skeptical about the resource question. I wouldn't bank on it. I'd bring my water if I were you. But from a science perspective, to give you an insight about why this is important, maybe a good analogy is what we're learning from the Earth's polar regions. Now, many people know that the Earth in the polar regions contains a fantastic record of our climate history. And that's because you've got material from the Earth's atmosphere that's been sequestered inside bubbles, inside these ice cores. And you can actually analyze and detect directly what environmental conditions were going back in time. And that's kind of the analogy that I use in looking at this material at the moon. If we were to go to the moon and do the same thing, drill out these cores and take a look at the chemical and isotopic composition of these materials, it may give us a record about conditions in the solar system, like solar system climate throughout time. It could give us insights into how the moon formed. Or it could tell us that there's an active dynamic process involving water on the moon today. And that's why I find this question really interesting. So, I'll stop there. Those are two projects we're working on here for water on the moon and Mars. Think about Europa and Enceladus and all the other exciting targets, the rings of Saturn, which are almost 100% water. It's a fascinating topic. Thank you. Any other questions?
Does the magnetic field of Mars tell you the Mars core environment?
The core is, what we debate about is how iron-rich the core is. The degree of iron, it's almost certainly got iron. That's what happens when a planet forms and becomes differentiated over time. We don't have a lot of information about the composition of the core directly. And partly it's because, we don't live there. The field quenched and died. So that hints at whatever molten process that has this convection process that causes the magnetic field has really subsided. So I don't have a firm answer. The core of Mars is still a bit of a mystery. And there are other missions that are looking at that right now. In fact, the InSight mission, which was selected to put a seismometer on the surface of the moon, may give us some real insight into that question in the coming years. Go ahead.
Is one of the earliest slides shows the molecule of water with an angle of 104.45 degrees.
Yeah.
I read an article where somebody proposes that there's some water that can do magic things that has a different angle. Is that such a thing? Like water exists with a different angle there?
I haven't heard of it, but I will say water continues to surprise me. It has a myriad of states and conditions, and so when you're changing environmental conditions, who knows? But yeah, I haven't run across that yet.
Are you familiar with the Mars One project where they're
Yes.
proposing to?
Yeah.
And do you know? I mean, I don't know how seriously people take that, but do you know if they're proposing to take their water with them, or if they're hoping to find water there?
Yeah. mean, that's a good question. It gets right at the strategies for, settling Mars. We don't know enough about Mars right now to count on having what we call in situ resources. That is, resources there that you can leverage. If you were going to take a chance on that, I would say please land on one of the polar caps, in a place where existing remote sensing data tells you that it's 15 or 20% water ice, and then hope you get lucky. In terms of finding liquid water and drilling down and getting it, we've got very little idea. You'd really be taking a risk. If I were them, I would take the water at this point, or wait until we have much better data on Mars. So.
I saw on the LinkedIn you have a magnetometer on there. What are you expecting to find with the magnetometer?
Yeah, so I mentioned that Mars does not have a large-scale, intense global magnetic field like the Earth, but there are what we call remnant fields. These are portions of the planet's crust that have been magnetized, left over from when this large-scale field occurred, and they just happen to get preserved. And so we call these magnetic anomalies. And we're using them as little small laboratories to in fact see if this magnetic field makes any difference in atmospheric loss processes over those regions. And so we need the magnetometer to measure that. We also need the magnetometer because the manner in which the solar wind interacts with and strips off atmosphere around Mars is partially dependent upon the direction of the magnetic field. So it's like knowing, I don't know if I can find an analogy with the,
We were just looking for the global magnetic field though at the site.
So we know there's no global field, but we're looking at, the local fields over the magnetic anomalies.
What kind of magnetometer is it?
It's a typical flux gate design. Yeah, and it goes to fairly low frequencies. If we went to higher frequencies, we'd fly a surge coil, which is wire. But this is a low frequency flux gate. It's very much like what you deploy in a geophysics survey, but it's been miniaturized and made ready for space. It's about that big. And there's two of them on the solar panels, which is not a great place for a magnetometer because the solar panels are generating currents, okay? So we told them how to wire the solar arrays to not do that. And we also have two, so you can subtract out to a certain degree spacecraft interference.
What's known about the tectonics of Mars in the very early days?
There's one researcher, in fact, the principal investigator for the magnetometer, who has proposed that there's evidence for plate tectonics. And he is basing that on the structure of these magnetic anomalies, which have some of them have a linear structure. Still controversial. That's the only evidence I know of. Deep in Mars history, when it was maybe warmer, and you had more planetary differentiating happen with the cross-mantle activity, maybe. The big feature on Mars is this dichotomy. The southern and northern hemispheres are, it's almost like taking two different sized spheres and sticking them together. One is much more higher than the other. And that may be more important than the kind of question, yeah.
You heard about this region on Mars, it's thought to be an ice sheet covered by dust. It's very, very flat. I don't think it's near poles, or the North Pole, I don't know what it's called. I think that American spacecraft detected methane in the atmosphere of Mars, and the European spacecraft pinpointed that region. I'm wondering what you think about it.
Yeah, that's a compelling picture, isn't it? Right, because you've got water ice. I just talked about water and life, and you're bringing up methane, another volatile, by the way. This time, hydrogen is partnering with carbon, and there are two sources of methane. One is geologic, the other is life. So when you find water, methane together, wow, right? Here's the bad news: Mars Science Laboratory, which, incredibly enough, flies yet another version of one of those neutral mass spectrometers I've showed by the same guy. It's on LADI and MAVEN and MSL. Good business if you can get it. It is the most sensitive measurement of methane we have on Mars. It uses a tunable diode laser tuned exactly to the methane molecule. It's parts per million sensitivity. No trace of methane. No trace. The earlier measurements they had a lot of noise. They were remote sensing. There's a lot of uncertainty. I looked at those results and said, I'm not a methane spectroscopist, but that looks like noise to me. So, the earlier measurements were controversial. Now it's possible that the methane could be episodic. There could be transitory processes, so we don't expect to find it everywhere all the time, and the curiosity rover just could be unlucky. Yeah, and then as far as the ice, dust-covered ice, I don't know that region in particular. I wouldn't be surprised if it exists. And that would be a really compelling target for a land and do more investigation. So that's the extent of my knowledge on that one.
So, I didn't know previously how important these magnetic fields were in terms of protecting against water loss.
We think.
Okay, well, do you know if we have, like all these Kepler detected planets and so forth, do you know if we have any way of so far away detecting magnetic fields?
Great question. I've got a colleague up at the Space Science Laboratory whose hobby is that question. Because you're hitting the nail on the head. What you want to do, now you're flying all these extrasolar planets, you want to understand the attributes they have that could be conducive to life. And some people use the spectra from the entire disk, and it's average over the whole disk, but it's kind of like a water signature, not the, and your question is, the answer to your question is maybe, because what a magnetic field does is it organizes the charged particles around the planet. And that can cause the planet to emit in certain radio bandwidths. And in fact, I've worked on one of those called auroral kilometric radiation, AKR. Okay, it's a fancy name. It's radio waves from a laser-like process happening in space that's organized by planetary magnetic fields. So if you had coherent emissions like that, you could attribute that to this magnetic field geometry. There's also certain emission lines visible if you had enough sensitivity and you had a bright enough aurora borealis. Okay, the aurora happens in a ring around the poles because that's where magnetic field lines converge. So those are some ideas that look at.
What about other elements such as nitrogen and carbon?
Yeah.
Any effort to detect those?
Around Mars or?
Yeah, around.
Yeah, so as I said before, we were looking at the loss of CO2. Most of the carbon probably, although some carbon may have escaped, some of it, goes back into Mars. And in fact, the follow the water strategy of Mars has been replaced now with follow the carbon. So that's an open question. Some of it can escape. If it is, we'll see it on May. We have the capability to detect it. Oxygen as well, because there's a lot of oxygen floating around, bringing the upper ionosphere as O2+. So.
Jumping to Europa.
Oh no, wait. I'm stuck inside the asteroid belt today. So. Go ahead.
It has lots of water, and
We think.
have a magnetic field.
It doesn't have its own magnetic field. The reason why we know that there's water there is in fact because changes in the Jupiter magnetic field, the Jovian field, induce currents, electrical currents inside Europa that sets up a secondary magnetic field. So it's a transitory magnetic field that's induced by this big Jovian one. And we can tell by the properties of how that field decays with time, the fact that the inner layers must be highly conductive, and water is one of those things. That's our evidence for water on Europa. So there the volatiles and magnetic field are, again, tied together. Yeah.
The surface is supposed to be water ice.
The surface is definitely water ice, that much we know. And the question is it a thin shell of ice over a deep, thriving ocean, or is it, not so warm inside, not so conducive to life, some kind of, thin partial melt boundary, who knows, is it some dirty sludge, it's partially melted. We don't know a lot about the detailed structure of what it is, whether it qualifies as ocean or not. So similar question for Ganymede, by the way. And Ganymede may be more of a candidate for the sludge I talked about, but who knows, we got to go there more often, take a better look. Okay, thank you. Thank you. Heavy water, that tells you that's probably pristine early solar system material, down to its native quantum mechanical abundance of heavy water. These are called isotopes. And so this enrichment in heavy water is something that's important to understand because that gives us an immediate clue.
What did you mean when you said quantum mechanical?
There's a certain natural occurrence of heavy water that you find in the solar wind and what we believe to be the earliest solar system conditions. And to answer that question is a whole other talk. But we try and establish a baseline for what the earliest material was, and then we move from that. Okay, so let's take a quick walk through the solar system, just to give you an idea about various states and conditions under which we find water. This is Venus, and it turns out, unsurprisingly, there's a small amount of water vapor in the atmosphere of Venus. And incredibly, the amount of heavy water in that atmosphere is 120 times what it is if you look at water vapor on Earth. And what that tells us is that at some point in the past on Venus, there was a massive loss, a massive exodus of water as that planet evolved. That's the implication. When I talk about the Earth, we all live here, we know about it. The Moon, as some people may know, has recently been proven to have water ice, and I'll talk in detail about that. Mars has fascinated humankind for a long time in terms of the potential for water in the past and water that's present now. And of course, we do know that Mars has water, and I'll talk in detail about that as well. Interestingly, on Mars, it has about 5 times the amount of heavy water as you find on the Earth. And that hints at the ability or the prospect that Mars also, over time, lost its water through some process that we're trying to understand. The giant planets, gas giants, Jupiter and Saturn, they have water vapor in their atmospheres. And it looks like to be very pristine from the earliest solar system. It had very little processing at all. And then life gets a lot more interesting when you look at bodies like Europa and Enceladus. Those are moons of Jupiter and Saturn, respectively. Europa is a fascinating melting percent. But helium's problem is that it likes to be alone. It's very non-reactive. It's an inert gas. So you go down the periodic chart, and one really plentiful element is oxygen. And the other thing that oxygen likes to do is it likes to bond to things. Oxygen is very reactive. So it's actually no surprise that the most plentiful element in the universe and one of the more plentiful and, more importantly, more reactive elements form a bond and form this common compound. You can probably say that a similar story about other things like CO2 and others, but water is pretty special. It has this sort of dipole electrical property that makes it kind of semi-sticky. That's why you look at it in its fluid form and it behaves like it does. And it was also, like I said before, one of the first things to condense out of this protoplanetary disk and form the snow line. So it's formed an important role in planetary formation. Something that I need to get across to help you understand where we're going to go when I talk about Maven and Laddie is the detailed structure of water and a certain variant of water. So that has to do with how hydrogen atoms work. And a hydrogen atom is pretty simple. It's a proton and electron, the simplest and most plentiful element. There's kind of a variation on the hydrogen atom. It's deuterium. And deuterium is just like hydrogen, except that it has an extra neutron. It's fairly rare. Okay, something like 0.01% of water on Earth, you'll find a little bit of what we call heavy water. Okay, it's heavy because it's got an extra material in its nucleus. It occurs naturally. And this tells us a number of things. It can tell us, for example, what the temperature was when the water formed. We can tell that by the amount of heavy water that's in a sample. And the amount of heavy water in a sample can also tell us something about how water has been processed over time. And that's because they're chemically very similar, but this one weighs a little bit more. And that mass difference turns out to be important. And so if you come across a sample of water that has a lot of heavy water, that tells you that you probably lost a lot of water. And statistically over time, the lighter stuff left more easily. If you find a sample that's low, thanks folks. It's a really exciting time in this particular area. There's a lot of things going on right now involving water on the Moon and Mars and the kind of research and tools we're bringing to bear. Some of them happened at 4 a.m. this morning when one of the missions I'm going to talk about did a maneuver. I was glad to check my email and make sure that it went okay. So this is about water, and water is an important and interesting question as we explore the solar system. and ask ourselves questions about where life came from. And I'm being reminded by our guys to turn on the microphone. Is that better? Yeah. Okay, thanks. So part of this is a story about water, and just a little bit about where it might have come from and how it originated and how it distributed itself around the solar system, in addition to Earth, and some of the missions and scientific observations we're using to try and understand its dynamics and its importance. We all know that water is important on Earth, and so I hope to educate you some really specific detail about two planetary bodies, the Moon and Mars, as well as kind of give you a tour around the rest of the solar system to show you how commonplace and interesting this particular compound is. So, one of the prime motivations thinking about water is because, as many people understand, it is essential for life as we know it. All the life that we've understood here on Earth involves water. And where you find liquid water, life flourishes in almost any extreme environment, from the bottom of the ocean up to incredibly salty and or acidic tide pools, isolated locations where you have very cold water, you find life. Water is the thread that runs through all of that. So it's an astrobiology question to some extent, but it's also an environmental one and one that we can measure using physical techniques. It's also, from the perspective of agencies like NASA, an important resource. And if you believe in the idea that at some point humanity is going to expand into the solar system, you want to take advantage, ideally, like earlier explorers on Earth, living off the land if you can. It's really expensive and difficult to bring heavy things like water with you. And so the idea of using resources that are already there on the Moon, or more likely, maybe on Mars, and understanding where water is and what state it's in is important. So the way to think about water in the solar system is that it holds some clues about life, and thus our own origin, and also, if you believe that we are going to expand, about our destiny to a degree. So that's why I found water interesting. It's a great theme that runs through all these fantastic questions and touches upon science and exploration. So now that we've got the feel-good big picture down to the nitty-gritty, how do we do it? What kind of questions are we able to address at this point in humanity's exploration of the solar system? I'm going to talk about two missions that are examples of this. One is called MAVEN. That stands for the Mars Atmosphere and Volatile Evolution Mission. The volatile part is where the water fits in. Water is a volatile compound. It goes from solid to liquid to gas and back again pretty dynamically. And another one that's going to touch upon the water question for the Moon is called LADEE. That's called the Lunar Atmosphere and Dust Environment Explorer. Now, I said the word lunar and atmosphere together. That may be a surprise to some of you. The Moon does have a tenuous atmosphere. I'll talk about that. And both of these have pretty strong UC Berkeley environment involvement, so I can describe to you what we're doing here and up at the Space Sciences Laboratory to help these missions along. So before I talk about those, let's take a quick go back in time to, well, what we think might have been the beginning of the solar system, when we were just a big plane of gas and dust, a protoplanetary disk, early young sun in the middle, all kinds of gas and dust and little planetesimals around that will eventually coalesce and form the planets as you know them today. Every bit of evidence we have says that water was really commonplace in this environment. And the interesting thing about water, H2O, is that it was one of the first to condense out of gas. And it formed this thing called the snow line inside this big disk of gas and dust. And that was probably, I mean, again, we can't be sure, but roughly at around 5 times the distance from the Earth to the Sun is the position of the snow line. And so that had a big bearing on how the planets formed, both within the snow line and beyond the snow line in terms of their supply of water, what kind of water they got. But everything we know says that water was pretty common. And so we know the situation today. We are fortunate.
Where does the evidence for that snow line come from? I've never heard of it. Is that mathematical analysis?
It's a combination of looking at the composition of the oldest objects we know about, comets, okay, Kuiper Belt objects. It's modeling, it's the sum totality of everything we think we know about how planets form, looking at asteroids, So it's by no means completely certain, but it's our best understanding today that there was this idea about the sunlight. Maybe we can, get better with extrasolar observations. We'll catch these protoplanetary disks in operation. That would be some confirmation. So then, moving ahead to where we are today, we've got the best example where we are right now. Pointed out earlier, lots of liquid water outside today. The Earth is unique because we're in this region called the habitable zone. That's where water exists in all states, as an ice, as a liquid, as a vapor, and it goes back and forth between those pretty readily. We have a lot of water on the Earth, but the rest of the solar system, not so much. Liquid water is turning out to be fairly rare. It's easy to find examples of water vapor, water ice, but the amount of liquid water we have here right now seems to be somewhat unique. So let's think about water. You ever wonder how it got here, where it comes from? Well, we have a lot of it. Certainly we take it for granted. Let's think about water itself. Most people know water is H2O. You ever wonder why this really important substance is H2O? Hydrogen and oxygen? I don't know. I started to think about it. I thought, okay, well, let's look at hydrogen. That's actually pretty easy. Most of the universe, most of the material we know of is made of hydrogen. It's very common. 75% of the material is made of hydrogen. And the next most common element, helium, okay, the other 20